Hi, Sea Kings. So this is the beginning of chapter 10 for us. We're skipping chapter 9 for reasons that don't make sense anymore. But anyways, these notes are posted to Edmodo, and you should print them out before you listen to the video so that you can mark anything on your set of notes that you want to. So the topic is the fundamental counting principle, factorials, permutations, and combinations. Essential question 32 is, what is the fundamental counting principle and when do I need it? 33 is, what is a factorial and when do I use it? 34 is, what is a permutation? And give examples of situations that require a permutation. And 35 is, what is a combination? And how is a combination different from a permutation? So you can see in the left margin here, we're starting this chapter is about probability. So I wanted to give you some background definitions of some words that I'll be using in the examples. So in probability, an event is quantified by the number of ways or outcomes the event could occur. For example, a coin toss has two outcomes, either heads or tails. And there's more about that on page 539. Also, the fundamental counting principle states that if one event can occur m ways and a second event has n outcomes, then the number of outcomes of both events is m times n. This is true if you have 3, 4, 5, 6, however many events as well. So there's more about that on page 570. I've taken this example from 10.1, example 1. So you flip a coin and roll a 6-sided die. How many outcomes are there? So the first event is the coin toss with 2 outcomes, as we mentioned. The second event is rolling the die with 6 results because it's a 6-sided die. If it was a 12-sided die, there'd be 12 results. So according to the fundamental counting principle, there are 2 times 6 or 12 outcomes. And then I have another example similar to that one. Assume that your favorite color is green and that you have 2 hats, 7 shirts, 5 pair of pants, and 3 pair of shorts in complementary shades of green with coordinating patterns. So we're not going for paisley and plaid here, even during a lockdown. So how many outfits do you have to choose from? So you have 2 hats or no hats, because you could also not wear hats, that would be okay. And so that's 3 possibilities. There are 7 shirts, so that's 7 outcomes. And then you have 5 pair of pants and 3 pair of shorts, so that's 8 options there. We're assuming that the weather permits shorts because they didn't say it didn't in the instructions. We're also assuming that you're not choosing to wear pants and shorts at the same time. So by the fundamental counting principle, we have 3 events here. So that would be 3 for the hat, no hat situation, 7 for the shirts, and 8 for the pants or shorts. So that gives us 168 outfits. In the left margin here, I've got the definition for what a factorial is. So n factorial is written n exclamation point and indicates the product of whole numbers, so no fractions here, from n down to 1. So n factorial equals n times n minus 1 times n minus 2, dot, 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 down to 2 times 1. So I've got an example here of 4 factorial. That just means 4 times 3 times 2 times 1, and that equals 24. Please note that 0 factorial equals 1. That's always true, not just in our Algebra 2 class. And I want to show you that button on your calculator, or on my calculator. So on my calculator, when I turn it on, and if I hit 4, right, then my factorial button is under the probability button. So it's the 3rd option you can see. So I had typed in 4 already. I chose option, the 3rd option for the exclamation point, and that gave me 24. So you maybe don't have the same calculator, but there should be either probability or just an exclamation point as one of the secondary options. Okay, so this is an example that I made up for you just so we could use factorials. So the example is you manage a co-ed baseball team, the stay-at-homers, with 13 players. How many batting orders are possible if all 3 pitchers bat? So there are 13 possibilities to bat first, and 12 possibilities to bat second, and 11 players to bat third. So it's like the fundamental counting principle with diminishing possibilities, which is a factorial, right? It decreases by a whole number every time. So 13 factorial equals 6,227,020,800. And yeah, like I didn't multiply this out. I used the button on my calculator. So if you're curious about that. So I put in 13, I've got to my factorial, and that's the number that I got. All right, so I've got a second part here. It says, how many batting orders are possible if you want Flynn to bat third, followed by Blake, and then Casey? So in this case, I've already locked down 3 of the players, so that means I only have 10 factorial to consider, because in that third place, I know I only want 1 guy, which happens to be Flynn, or girl in my team. In the fourth spot, I know I want Blake to bat, and then in the 5th spot, I want Casey to bat. So I only care about the first 2 players, who's going to bat there, and then 6 through 13. So that gives me 10 factorial. And again, when I plug that into my calculator, I get 3,628,800. So hopefully all of that makes sense. Another definition I want to give you, a permutation is an arrangement of objects in which the order is important, such as a password. 1, 2, 3, 4 is a different password than 4, 3, 2, 1. So I would circle the P here for password and the P for permutation, just so that I put these ideas together. There's more about that on page 570 of your textbook. Also, the number of permutations of n objects taken n at a time is n permute n, which is n factorial. So if you're choosing all of the things that are available, then in a permutation where the order matters and it has to be different, then that's the same as a factorial. And so I've got 2 examples here that kind of talk about that. The number of permutations of n objects taken r at a time, when r is less than or equal to n, is n permute r, and that's n factorial divided by the difference of n and r factorial. So there's a button on your calculator for that as well. It happens to be, so you would put in the larger number. So say we've got 9 things and we want to permute 4 of them, just as an example. That gives us 3,024 possible different orderings of 4 of the 9 objects that we have. Okay, so our next example is 10.5, example 1. It says, how many permutations are there of? So A, I picked the composer Bach. He's got 4 different letters in his name. They're all different, none of them repeat. So that's 4 factorial, which is 24 permutations. I picked the composer Mozart, and so he's got 6 different letters. So there's 6 different letters to permute, which is 6 factorial, which is 720 permutations. And then I also chose the composer Beethoven because it's got 9 letters, but some of the letters repeat. So the E's take up 3 letters that aren't unique or distinguishable. So we've got 9 letters, but 3 letters repeat, and those are the E's, as I mentioned, which means we will have overcounted, right? Since 9 factorial is a product, we have to divide by 3 factorial to avoid overcounting. So 9 factorial divided by 3 factorial is this crazy number, or 60,480 permutations. So this situation is similar to that because if we've got 9 letters minus, so 9 letters minus 6, 6 being what we're choosing at a time, that gives us the 3 factorial that we divided by. So hopefully that makes sense. If not, you can message me on Edmodo during our scheduled class time. Next up, a combination is a selection of objects in which the order does not matter, like a hand of cards. Not like a combination lock. That would be a permutation because that's a password. So I would circle the C from the cards and the C from combination so that I remember as my mnemonic device that a combination is like a hand of cards and the order doesn't matter. And there's more details about that on page 572. So this example is from 10.5 example 2. There are 10 horses running in a race. In how many ways can there be a first place, a second, and a third place if there are no ties? Now, we know that first place, second place, and third place are different. So this isn't a combination. This is a permutation where the order the horses cross the finish line matters. So there are 10 horses, so n equals 10. There's a first, second, and third place, so r equals 3. So we want 3 of the objects out of the 10 horses racing. We are using a permutation because the order in which the horses cross the finish line is important, aka a gold medal does not equal a bronze medal. And so using 10p3 in my calculator, I get 10 factorial over 10 minus 3 factorial, which is 7 factorial. Again, I really just want you to use the button in your calculator, so I'll show you that. So we said we had 10 p, choose that option, 3, and that gave us 720 possible ways that out of those 10 horses at the finish line, 3 of them would come in first, second, and third. So that's that example. I also wanted to tell you the number of combinations of n objects taken r at a time, where r is less than or equal to n, is NCR. We tend to say n choose r, and that's n factorial over n minus r factorial times r factorial. So the whole denominator is kind of complicated. This is on page 572. NCR is read N choose R, and there's a button for that on your calculator as well. So on 10.5, this is like example 4, kind of. It says, how many combinations are there of the cards? 2 of diamonds, 4 of spades, 7 of clubs, and the queen of hearts. So if you're dealt the above cards, the order in which you receive the cards doesn't matter, so there's only one combination. Does that make sense? So however these cards are dealt to you, the order doesn't matter. It's still the cards that you have in your hand to play whatever game it is you're playing. So that's why we're talking about a combination here and not a permutation. Also on this other page, I did, in the event that you don't play cards in your family, that's just not a tradition you have, a deck of cards has 4 suits. 2 of them are red. Hearts and diamonds are red, and spades and clubs are black. And each suit of cards has from ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So there's 13 cards here. 13 times 2 would be 26 if we're just talking about red cards, or we're just talking about black cards. And 26 plus 26 is 52. So a deck of cards has 52 cards in it. Okay, so lastly, I want to tell you about 10.5 example 5. So you order a sandwich to go, of course, and you have 8 side dishes to choose from for your 2 sides. So the way that you order the sides doesn't matter. So this is a combination and not a permutation. And so we would use 8 choose 2, which is 8 factorial over 8 minus 2 factorial times 2 factorial, or 8 factorial over 6 factorial times 2 factorial. But I don't really care. I really just want you to use the buttons on your calculator. So we have 8 Can you see this? Is this on the screen? And then choose is my second option. On this particular calculator, we've got 8 side dishes. We're going to choose 2 of them. That means there's 28 possible sandwich 2-side combinations available from this restaurant's menu. So we've got 28 combinations there. So I hope that that makes sense, and I will be available for your questions tomorrow during our scheduled times. I'll be on Edmodo. You can message me. Thanks so much. Talk to you soon.